All right, I want to go over a couple of quick theorems about modular congruence. The first one is if you have two numbers and A is congruent to B modulo some specified number m, that's true if and only if A is equal to B plus a multiple of m, okay? A equals B plus km for some integer k. Now, quick proof of this, let's go forwards. So assuming A is congruent to B mod m, the definition of that is that K divides A minus B, right? And the definition of this, K divides A minus B, is that A minus B is some multiple of, actually, I'm sorry, this should be, I apologize, this should be M divides A minus B. If they're congruent mod m, then m divides A minus B. So A minus B is some multiple of m, and that multiple is the number k. So that's for some k in Z. But then, as you can see, you can just add B to both sides and obtain A is equal to B plus Km. So check. That proves the forwards direction. The backwards direction is just as easy, and I'll leave that as an exercise to you. So you can go ahead and try proving the backwards direction of that implication to show that these are indeed equivalent. Now, so that's my the first theorem I want to mention. Now, the second theorem, it has to do with congruence as well, but it introduces a few more numbers. So if A is congruent to B mod m, and C is also congruent to D mod m, so we have four different numbers. A and B are congruent to each other mod m, C and D are congruent to each other mod m. So it has to be the same modulus, right? You can't have like mod 5 over here and then mod 7 over there. Like, no, it's got to be both the same. But if these two are congruent and these two are congruent, then it turns out you can, it's kind of obvious, but you can add A and C, and you can add B and D, and those resulting sums are going to be congruent to each other, because it's kind of like saying A is equivalent to B and C is equivalent to D, so if you take the A and the C and combine them, it's equivalent to doing the B and the D and combining them. I mean, it sounds kind of obvious, but is it obvious? Let's prove it. So I'll write it out. A plus C is congruent to B plus D, modulo m. As a quick proof of this, if this is true, if these are true, if A is congruent to B and C is congruent to D, then we can say that first of all, that A is going to be B plus K1M using the previous theorem. Okay, I'm going to use this version here. So A is going to be B plus some multiple of M, and C is going to be D plus K2M, and this is for some K1 and K2, right? Then we can do, with these in mind, you can do A plus B and obtain from that, by substitution, B plus K1M plus D plus K2M. Then you can kind of rearrange some things, B plus D plus, and then take the K1M and the K2M and factor out an M to get K1 plus K2M. So this probably feels kind of familiar, because this is pretty similar to the proofs you did in chapter 1, that were things like, hey, if you take this and add this, then if you take an even number and an even number, you can add them and get another even number, right? Or if you take like an even plus an odd, then it's always going to be an odd or something like that. So it's kind of a similar sort of approach, and you end up saying, hey, here's a number plus a multiple of this other thing. What we've shown here is that A plus B can be written as B plus D plus a multiple of M, and so therefore they're congruent. Now, it turns out this is true not only for addition, but also for multiplication. So 2, A times C is going to be congruent to B times D mod m. And again, I won't take the time to prove that, but you can do it very similarly by, take as given these two facts, right? A is B plus a multiple of m, and C is going to be D plus a multiple of m. You can multiply them together and show that the result is going to be B times D plus a multiple of m. And therefore, these two products are also congruent. So again, proof left as an exercise for you to try on your own.